Okay, so today we're going to be discussing homework 4, which is going to cover the LSTM-RNN with a DNN classifier and finding out how adding a word embedding layer in various forms affects performance. So to go through the code first, we've got our import statements, and some of this is left over from homework 3 that I copied over since there was a lot in common. So we'll just skip over those parts. So we've got our one thing that's different that we had to take out is the one hot encoder generator that was there. And because we're no longer going to be using it, instead we're going to be replacing it with just the tokenizer. Or yeah. And so we're going to be using the Twitter US Airlines Sentiment Database, and which is the same as previously. I changed a couple things around here from the last. I actually used post padding for most of this, but I also toggled it back and forth. It didn't seem to make much of a difference. Once again, the data, as I pointed out in Project 3, the data is imbalanced and highly imbalanced. This imbalance in this project, I dug into that a little bit further. I didn't do anything to mitigate it. Most specifically because I wanted to see how the data could be altered to try to sort of jump over the imbalance issues and see how far we could get with it. We did our train test split. Here's our build. The difference being here that we added our embedding layer. And here we're passing in our dimensions, which is 100, our vocab size, which is 15,770, and we are making it trainable, of course. So we've got our LSTM layers here, and an option to have more layers. We've got our dropout designated here if it's one of the parameters, if it's not 0, and we've got additional dense layers if there are dense layers that are added, and then finally we've got our last output layer dense classifier here, and we're using RMS prop for optimization. We're using categorical cross entropy for to calculate loss. And I didn't experiment with any of that. And softmax for the final classification, ReLU inside of hidden layers, hidden DNN, additional DNN layers, and TAN activation inside of the LSTM layers. So I didn't make changes to those. I just made changes to these parameters, which are the number of LSTM layers, the number of additional dense layers beyond the classifier, dropout rate, number of units, learning rate, L2 regularization, and then these remain static for all models. And so I use this, we'll come back to this. The primary focus of this assignment was to use the same parameters from Project 3, which are listed here, but I wanted to dig a little deeper into to prove some additional patterns that were discovered. And we'll go into that later. Okay, so this is the training, and it's the same as what I've done in the past. And then this is the parameter grid to use for the specific project 3 parameters that were used, the best parameters for the best LSTM model. And here's our training session printout and the model summaries. We've got our loads and saves, plot history, plot loss, and then that's stuff that needs to be deleted, and then that's for further analysis later. Okay, so going over here to our report, the part that I think I'd like to talk about, because I can't talk about all of it, is this last portion here, and that's where I used the random parameters, and these so I wanted to see the pattern that emerged is that when you looked across the average validation accuracy across all epochs, there was, albeit very marginal, a consistent increase from the base LSTM model to the from scratch model to the Glove frozen weights model, and also to the tuned Glove embedded layer. As you can see, the values are here: 79, 7911, 7973, 8109. So this is not enough to prove that there's a pattern, because there's fluctuations in different runs of the same model with model configurations, and so I wanted to come up with a strategy to prove that aside from the changes in hyperparameters, you could see behavioral shifts for the primary architecture. And the primary architecture I'm referring to as the base, scratch, frozen, and tuned. And the hyperparameters are these that I've discussed here. And so I wanted to see if hyperparameters are responsible for the changes, or the base architectural builds are responsible for the changes, and by evaluating numerous models and aggregating those scores across the top models, seeing if the patterned increase in validation accuracy, average validation accuracy, was consistent beyond the individual model configurations that were tested in this assignment. So here you can see, so if we come down here, we have a comparison of the original value that was from the experiment, and I called this the stress test. And so this is the stress test score for the base model, and as you can see, the values are fairly similar, and the distance between the values is also fairly similar to the original distance. So this really confirms that there is, although it's very marginal, there is a patterned increase from the base model to the fine-tuned model. And this, if I'm not explaining it very well on this video, the explanation is very detailed in the report. So also, I wanted to look at the standard deviation between the scores of all the top 6 and the bottom 6 models, and between all 12 of those models, the standard deviation, so best case scenario and the worst case scenario, the standard deviation was only 0.014 for the base model, 0.013 for the scratch model, 0.012 for the frozen model, and 0.008 for the tuned model. So as you can see, as well as their values being low, meaning that there's not a lot of variation between the worst case performance and the best case performance, and this is shown to be consistent by evaluating the top 6 and the bottom 6. So in addition to there not being very much variation, also supporting the patterned analysis being the result of standard results as opposed to independent or individual variations within the data sets or the specific trial. In addition to that, you can see that there's a decrease, again, extremely marginal, but a decrease in the standard deviation that follows the pattern of the increase of average validation accuracy. And that suggests that during these major architectural shifts, not only is the best performance improving, but also the worst case performances are improving as well. And so in the end, we were able to prove, even with marginal differences, that these marginal differences are relevant to suggesting architectural changes between that were explored in this study, and suggests further that the data set level constraints, such as class imbalance or ambiguous labeling, which we showed up here and discussed up here, may have more to do with the ceiling. Sorry, how did I refer to it? Anyway, the upper end of performance seems to be throttled by something, and it may be due to the data set itself and this imbalance and these ambiguous labels that are included. So to further this study, and what I would suggest further on to myself or otherwise, would be to either use a balanced data set, just replace this data set with a balanced data set, or to look into data balancing methods. And I looked into those some to see, to start sort of the conversation with myself about what those are. And but I didn't find anything that looked super promising so far. So I'm not sure what the best approach is for that yet. All right, I am over time as usual. I'm exhausted as usual. And I will conclude this. Thank you. I worked very hard. I hope you consider that. Bye-bye.